Hey guys, Mr. B here. In this video, we're going to be going over the chapter 26.3 notes on the life cycle of stars. So this video is primarily just me going over the information. So if you learn better this way, hopefully this will help you. All right, let's get into it. So how do stars form? Where do they come from? All right, so we know that in space, there's lots of material that's just kind of floating around. In some cases, there's lots of stuff kind of all clumped together in more of a cohesive unit. We call these things nebulas. Okay, it's a large volume of gas and dust and other material that's kind of just hanging out in space. And we know that in these regions of material, there's some parts where there's material that's more closely dense, it's more close to each other than other places, and so there's more gravity. Okay, and so over time, as these denser regions, which there's more gravity pulling stuff in, continues to contract, gravity will continue to get stronger, continue pulling more and more stuff in. And as this happens, this material is going to get smushed together. It's going to get denser and denser. But between all the collisions and friction, it's going to start to heat up. And we start forming what we call a protostar. Okay. Now the word proto means before. So you may have heard the term like a prototype, right? A prototype is like, something before your final product. So protostar is before a star forms. It's what we have. Basically, this material is clumping together. It's getting denser and denser. It's heating up. It just hasn't quite started doing nuclear fusion yet. So until it starts to do nuclear fusion, until the atoms in there start to smash together to make new ones, it's not a star yet. Okay, but it's getting there. It's very close. Now, eventually, over time, as it continues to contract, as gravity continues to crush it and bring things closer together, eventually it will become dense enough and gravity will become strong enough that those atoms will fuse together to make new atoms, and nuclear fusion will begin and it will ignite. And at that point, we consider it to be a star. Okay. Now, this takes a very long time to happen, thousands or millions of years. So it's not like we can just take pictures and just go, hey, look, there's a star that just formed. Oh, there's another one. And we can videotape it. Takes a very long time. But we've taken images of lots of different nebulas with stars forming in different stages. And so we can kind of put them all together and take a look and see we can see how stars can form because this one is just forming and this one's a little bit further along and this one's closer and now it's a protostar and here this one now a star has formed. We can kind of see that picture by taking lots of pictures of nebulas and kind of putting the pieces together. Okay, so that's essentially how stars form. Now, I'm not going to be going over the questions here. I have a whole video of me going over the questions. So if that's something that you're interested in, you can go watch that to make sure you're doing them right. I'm just going to keep on going and talking about the information. So once a star has formed and it's considered an adult, how long is it going to be on the main sequence for? Now, there's one primary factor that determines how long a star is going to live and what it's going to do, and that 100% comes down to how much mass it has. Okay, how big is it? The mass of a star is the sole factor on how long it's going to live, what it will do when it dies, and all of that stuff. Okay, so there are typically high mass stars, average mass stars, and low mass stars. High mass stars are usually going to be the bluest, which is the hottest. Okay, remember from the last chapter section, blue color, blue flame is the hottest flame. So high mass stars are usually going to be the hottest and the brightest of main sequence stars. They're the brightest because they're the biggest, and remember that the bigger they are, the more surface area they have, the more light they can give off. Now, the trouble though with high mass stars is because they're so big and they're burning so hot, they usually only last a few million years. Now you might think to yourself, well, a few million years, that's a long time, right? I mean, humans, we only live for 80 to 100 years, so a few million years, that's a really long time. It is. But in relation to the length of how long stars live for, it's not very long. Okay? The reason they die so quickly is because they're so big and hot. In order for them to not get crushed by their own gravity, they have to burn enough fuel fast enough to create enough thermal pressure to push outwards and balance out gravity. Okay? And the only way for that to happen is they have to burn a lot of fuel really quickly. So they essentially burn themselves out very fast. Whereas medium-sized stars, more like our sun, our yellow star, will usually live for about 10 billion years. Now that's a big jump of time. A few million to a few billion years, that's a very long amount of time. Okay, that's like being a millionaire compared to a billionaire. It's a lot of money difference between a million and a billion. So this is a very long amount of time that medium-sized stars live for. And that's because, of course, they don't need to burn their fuel as quickly because they're not as big. They don't have as much gravity. They don't need to like worry about making as much energy to overcome gravity from crushing them. And then even smaller stars, so like the red main sequence stars or like the dwarf stars, they can live for over 100 billion years, which is a very, very long amount of time. So just to give you a rough idea of how long it is, we estimate the universe is about 14.5 billion years old. And these small red stars can live for over 100 billion years. So that means that they're maybe 10 to 12 billion years old right now. They're like still babies, right? Like they're not even a fraction of the way through their lifetime. If they live for over 100 billion years and they're only like 10 billion years old. So they live for a very, very long amount of time. And that's again because they really don't burn through their fuel very quickly. So they just kind of, sit there and smolder for like a very long amount of time. Okay, so other than that, let's talk about star death. So eventually, of course, a star is going to run out of fuel. And when that happens, it's going to die. What's going to happen when it dies? Well, there's 3 outcomes we're going to be looking at here, okay? When a star dies, it can turn into a white dwarf, a neutron star, or a black hole. And these outcomes are, again, 100% dependent on how much mass the star has to begin with. So small and medium mass stars, like our sun, and pretty much most stars that are on the main sequence are medium mass stars. They're going to turn into white dwarf stars. Okay. Now, when they die, what's going to happen is the star itself will start to swell up a little bit. That's because it's going to start fusing together heavier elements, which take up more space, and so they start to expand, and it turns into a red giant. Then the outer layers of the star will kind of fall off. Okay, it's kind of weird. So it swells up like a balloon. The outer layers sort of fall off. Those layers turn into what we call a planetary nebula. So all of this gas and stuff on the star kind of falls off and it makes a giant nebula, and then planets and stuff like that will form from that material. And then what you have left after those layers fall off is pretty much just the core that's left over, which at this point is going to be what we call a dwarf star, a white dwarf. So it's very small. It's usually very hot and it's very dense, but it's not very bright because it's not very big, right? And again, brightness primarily is determined by surface area. So the bigger the star, the more light it gives off, and the smaller it is, the less light, okay? And then as a dwarf star, it'll just kind of sit like that for probably a few billion more years, and eventually it will just cool down and pretty much just turn into like a lump of charcoal and just float through space forever like that. Kind of sad, okay? So not super exciting. High mass stars, on the other hand, die in a way more spectacular fashion. So high mass stars like supergiants, as they run out of fuel, right, they have way more gravity. So remember, these big stars have lots of gravity trying to crush these things down. As they are running out of fuel, gravity eventually is going to win because they will no longer make enough energy to push outwards to stop gravity. So gravity is going to crush them down. And because they're so big and they have so much gravity, gravity is going to crush them down really fast, okay? And it's so fast that when the star collapses, it collapses so quick that it actually like inverts in on itself and it rebounds. So it's like, boom, goes down and it like inverts and rebounds. And when that happens, it goes, and it blows up and stuff goes flying everywhere. Okay, we call these explosions supernovas, supernova explosions. So gravity's super strong, crushes the star down really fast, so fast the star like rebounds in on itself, and then it just goes boom, and it just spews stuff everywhere. Okay, stuff just goes flying out in all directions, and it gives off so much energy and so much light it can outshine entire galaxies. Right now, after this explosion happens, you might think there's nothing left, right? The star's like blown itself to pieces. There's literally nothing left over. And that's where you'd be wrong. There actually is something left over after a supernova explosion. We call it a neutron star. So after this explosion goes off and all this material spews out in these giant rings, there is a core of the star left over. Okay, now the core has a mass that's less than about 3 times the sun's mass, so it's very, very small. It can be about the size of planet Earth, and it's made completely of neutrons. This is a weird concept, so this is a chemistry thing here, but you probably know that most atoms are made out of protons, electrons, and neutrons. This core that's left over is 100% made from neutrons, which is a really weird material, and it's super, super, super dense. Okay, it's very dense, it's very heavy. So if you took a teaspoon of it, that material would weigh like over 10,000 tons, right? Like it would be the heaviest material ever. It would be absolutely crazy. But this little neutron star is left over after the supernova explosion, and it just kind of sits there for a long time. Now, a lot of times these neutron stars can be spinning after this explosion happens, and they'll give off radio waves. So imagine it's sort of like a lighthouse where it gives off radio waves in 2 directions, and as it spins, those radio waves will point towards Earth and then point away from Earth, and then point towards Earth and then point away from Earth. So when we see it from Earth, it kind of looks like it's pulsing, okay, or it's pulsing as it gives off these radio waves. We call them pulsars, okay? So this is one outcome after a supernova. Now, if the star is even bigger or really big, not only will it blow up into a supernova, but the neutron star that's left over will have enough gravity that also will crush itself down to become a black hole. Now, this, of course, is very rare because most stars are not very big. They're about medium size. So most stars are going to end up as dwarf stars. A much smaller percentage, which are big enough, will blow up and go supernova and make neutron stars. And then an even smaller portion will blow up, go supernova, make a neutron star, and then that will crush down even further to make a black hole. And as most of you know, a black hole is basically a hole in space with very strong gravity that nothing can escape it. Now, there's one misconception that a lot of you may have about black holes, and that's that they suck stuff in, right? Like if you get near black holes, you're going to like just suck everything in. Doesn't work that way, okay? Black holes certainly have a lot of gravity, and if you get close enough, they will pull you in and you can't escape. But there is an area around a black hole that you can orbit around it, just like you can orbit around a star or anything else. It's just that you don't want to get closer than that, okay? So there's a radius that we call the event horizon. And as long as you don't cross that line and get close to the black hole, you can orbit it just fine, okay? But if you cross the event horizon, at that point, you'll be inside of the black hole's gravity to the point where you can't escape anymore. And then at that point, you're going to get sucked in, okay? So black holes, there are stars that orbit around black holes and other planets that orbit around black holes. We know that happens. So understand that they don't just like suck everything in, okay? But they do have very strong gravity, obviously, and you wouldn't want to get close to one. So again, so just to recap, medium to small mass stars will die and turn into dwarf stars. Larger stars will blow up and go supernova, and you'll have a neutron star left over. And if the star is even bigger than that, they'll blow up, make a neutron star, which then will collapse even further to make a black hole. Okay, so those are the 3 outcomes that a star can die as. And again, every single one of those is 100% dependent on how much mass it has. All right, so that is it for this section notes. Again, if you're interested in going over the questions, I have a video on that, so you can take a look at it. But otherwise, I will see you in the next section, which is chapter 26.4. Bye.